Tonight, the most precise timekeeping instruments ever built are going to tell you something that no one felt, no one noticed, and almost no one is talking about. On July 5th, 2024, Earth finished its rotation 66 milliseconds early. Not a second, not a fraction of a second most people could name. 1.66 milliseconds, a unit so small that it sits completely outside normal human experience. And yet, atomic clocks on 6 continents recorded it simultaneously, confirmed it, logged it, and noted that it was the shortest day since humans invented a clock precise enough to catch it. That is not the strange part. The strange part is that 3 other things are changing inside this planet at the same time. The solid iron core at Earth's center has reversed its rotation direction relative to the surface above it, a growing weak zone in Earth's magnetic shield. A region where the field is significantly weaker than anywhere else on the planet has expanded to cover an area roughly half the size of Europe. And the magnetic North Pole has abandoned its position over Canada and is crossing the Arctic Ocean towards Siberia at a speed 3 times faster than anything recorded before the 20th century. None of these are emergencies. None of them will affect your day tomorrow. But all of them are confirmed by peer-reviewed data published in some of the world's most prestigious scientific journals. And all of them are happening right now beneath your feet, in a planet most people assume has not changed in any meaningful way since long before any human was alive to measure it. Tonight, we are going inside. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. There is an institution called the International Earth Rotation and Reference System Service. It exists for one purpose: to monitor whether Earth is rotating on schedule. Every day, it compares the time kept by atomic clocks to the actual observed position of the planet, checks them against each other, and issues corrections when the gap between the two becomes too large to ignore. The fact that this institution exists all is worth sitting with for a moment. We built some of the most precise instruments in human history, pointed them at our own planet, and discovered that Earth's rotation was not reliable enough to serve as a timekeeping standard. We did not assume our planet was a perfect clock and find out we were right. We assumed it, tested it, and found out we were wrong. Wrong in a small way, but wrong consistently enough to require a permanent international organization, updated correction tables, and occasional manual adjustments to global timekeeping standards. Those adjustments are called leap seconds. They work like this. When Earth's rotation has fallen behind atomic time by a full second, a leap second is inserted into the official time record to bring the two back into sync. Since 1972, when the modern system of comparison was established, 27 leap seconds have been added, not evenly. 9 of them were added during the 1970s, when the planet was rotating relatively slowly. As the decades passed and Earth gradually began to spin faster, the additions slowed. The last leap second was added in 2016. No new leap seconds have been added since. The reason no new leap seconds have been needed since 2016 is that Earth has been gradually speeding up. When Earth runs ahead of atomic time rather than behind it, the gap does not require a leap second addition. It would eventually require a subtraction, something called a negative leap second, which has never happened in the history of the system. Clocks have never had to skip a second to stay in sync with a planet that was rotating too fast. Until the current trend, this was a theoretical scenario considered possible but distant. To appreciate what atomic clocks are actually measuring, it helps to understand what they are. An atomic clock does not tick in the ordinary sense. It counts the oscillations of electrons in atoms, typically cesium-133 atoms, which transition between two specific energy levels at a frequency of 9,192,631,770 cycles per second. This frequency is extraordinarily stable, defined as the basis of the international second itself. The best atomic clocks in the world neither gain nor lose a second over timescales of hundreds of millions of years. They are by far the most precise timekeeping instruments ever built by humans. When you compare the time kept by an atomic clock to the rotation of the Earth, you are comparing one of the most stable physical processes accessible to measurement against one of the most complex. The Earth's rotation is affected by winds, tides, ice sheets, ocean currents, fluid motions in the core, interactions with the Moon, and subtle electromagnetic coupling between its layers. It is a system of extraordinary complexity driven by forces operating on scales from kilometers to thousands of kilometers and on timescales from days to billions of years. The atomic clock is indifferent to all of this. It keeps its frequency regardless of what the planet is doing. The comparison reveals the planet's imperfection with a clarity that no earlier technology could achieve. Before atomic clocks, the best timekeepers were themselves based on Earth's rotation, which meant that any variation in rotation was invisible, absorbed into the definition of time. Atomic clocks removed that circular dependency. They gave science an external standard against which to measure the planet, and the planet, measured against that standard, has been found to be irregular. On July 5, 2024, the most extreme expression of that irregularity in the instrument error was recorded, 66 milliseconds short of the standard 86,400 second day. Several other days in 2024 on the summers of 2022, 2023 and 2025 came close. The trend is clear in the data. Since roughly 2020, Earth has been consistently completing its rotations faster than the long-term average, with the 2024 summer peak representing the most extreme expression of that trend. The instinct is to ask what this means for daily life. The honest answer is very little, directly. The days are not getting shorter in any way that a human body can detect. The mismatch we are discussing is measured in fractions of a millisecond per day. A full second of difference accumulates over years, not hours. What matters is not the direct human experience of the change, but what the change reveals about forces operating inside the planet that are otherwise completely invisible. Something is making Earth spin faster. Identifying what requires understanding what controls Earth's rotation in the first place, and how several very different physical systems all contribute to the same final number. Earth's rotation speed is not controlled by one force. It is a continuous negotiation between competing influences, most of them operating on different timescales and most of them pulling in different directions. The dominant long-term influence is the Moon. The Moon's gravity pulls on Earth's oceans, creating tidal bulges on the near and far sides of the planet. As Earth rotates beneath these bulges, the bulges resist being carried along, acting as friction on the planet's spin. This is tidal braking, and it is both well understood and relentlessly consistent. Over geological time, it is the primary reason Earth's day has been getting longer. About 100 million years ago, a full day on Earth lasted roughly 23 hours. About 4 billion years ago, it was closer to 18 hours. The early Earth, not long after formation, may have had days as short as 6 hours. The Moon has been gently slowing this planet's spin for most of Earth's history, and it has been gradually moving farther from Earth in exchange, its orbit expanding by about 3.8 centimeters per year as Earth transfers angular momentum into the Moon's orbit. Against this long-term backdrop, shorter-term influences operate. The atmosphere is one of them. Large-scale shifts in circulation patterns. The jet stream changing its position, monsoon systems, strengthening or weakening strong El Niño events, redistributing wind momentum across the tropics. All of these can measurably change the length of a day by small fractions of a millisecond. The effect is real and tracked. Meteorologists and geodesists work together to account for atmospheric angular momentum when they are trying to isolate other signals in the rotation data. Ocean currents contribute similarly, redistributing mass as circulation patterns shift with the seasons and with longer climate cycles. The seasonal loading and unloading of ice sheets as snow accumulates in winter and melts in summer imposes regular annual variations on the planet's moment of inertia and therefore on its rotation speed. All of these are understood well enough to be modeled and subtracted from the data when researchers are trying to isolate the deeper signals. Then there is the ice melt effect. And this is where the story of the 2024 record takes an unexpected turn. When polar ice melts, the water does not stay at the poles. It spreads across the world's oceans, flowing to lower latitudes. The physics of what this does to Earth's rotation comes from one of the most fundamental principles in classical mechanics: the conservation of angular momentum. The total angular momentum in a closed system does not change unless an external force acts on it. In a spinning system, If mass moves away from the rotation axis, the spin slows. If mass moves toward the axis, the spin speeds up. The figure skater is the standard example. Arms pulled inward, spin accelerates. Arms extended, spin slows. Arms extended, spin slows. Earth's rotation axis runs from the North Pole to the South Pole. Ice at the poles is sitting near the rotation axis. When it melts and distributes across the oceans toward the equator, it moves away from that axis, effectively extending the planet's arms, and by the ice skater principle, the rotation should slow. Duncan Agnew, a geophysicist at the Scripps Institution of Oceanography at the University of California, San Diego, showed in a 2024 paper published in Nature that this ice melt effect is real and measurable. His analysis found that without the slowing influence of ice melt, the record-setting short days we have been seeing would have been even shorter. The melting polar ice caps are acting as a partial counterweight, partially cancelling out whatever is driving the acceleration. The planet is speeding up despite having a brake being applied by its own melting ice. The way Agnew explained this publicly is useful. He described the situation in terms of the ice skater analogy. As the polar ice melts, the water spreads out toward the equator, which is like the skater holding their arms out. That should slow the spinning, and it is slowing it relative to what the rotation would be without that effect. But the overall planet is still spinning faster than its long-term average. Whatever is pushing the spin faster is winning against the ice melt brake. This is a finding with a double significance. It connects two of the major changes currently operating on Earth's surface and interior. Ice sheets are melting at the poles, and that melting is directly altering the rate at which the planet rotates. The planet's rotation is connected to processes in the deep interior. The deep interior is connected to the magnetic field. These are not separate systems. They are coupled, and what happens in any part of the system propagates over time to the others. Which means the acceleration is coming from something that is overpowering even that, something not on the surface. Something not in the atmosphere or the oceans, something that, by elimination and by physics, must be deep underground. The leading candidate is changes in the flow of liquid metal in Earth's outer core. The outer core is not sealed off from the mantle above it. The two layers interact through a mechanism called electromagnetic coupling, in which the magnetic field threading both layers transmits forces across the boundary. When the flow patterns in the liquid outer core shift, they can push or pull against the solid mantle, transferring angular momentum upward, and that transfer eventually reaches the surface and changes the rotation speed. This mechanism has been proposed before to explain rotation anomalies that surface processes alone could not account for. The current situation, with multiple lines of evidence pointing simultaneously to changes in the outer core and the inner core, makes the deep interior the most credible source of the acceleration. There is a secondary reason the rotation anomaly matters beyond the pure science of it, and it touches something more immediate: global timekeeping infrastructure. The world's navigation and communication systems depend on precise time synchronization. GPS satellites carry atomic clocks and broadcast timing signals that receivers on the ground use to calculate position. The accuracy of a GPS position fix depends directly on the accuracy of the time signals. Banking systems, mobile networks, power grids, financial trading platforms, and scientific instruments from radio telescopes to particle accelerators all synchronize to coordinated universal time, the atomic clock standard. When Earth rotation drifts from that standard, the gap must eventually be addressed. The solution, historically, has been the leap second, a 1-second addition to official time, inserted when the accumulated discrepancy between atomic time and Earth's rotation grows large enough to warrant it. 27 leap seconds have been inserted since 1972, but if Earth's rotation continues accelerating, the accumulated drift would eventually go the other direction. Atomic time would run behind Earth's actual rotation rather than ahead of it. Correcting for that would require a negative leap second, removing 1 second from the official time record. This has never been done. The software infrastructure that keeps global systems synchronized was not designed with negative leap seconds in mind. Some engineers argue that introducing one could cause software failures in systems that assume time always moves forward monotonically. In November 2022, the General Conference on Weights and Measures voted to retire the leap second entirely by 2035, allowing the accumulated discrepancy to grow without intervention until a future, larger correction becomes possible. The decision was partly motivated by the technical problems leap seconds cause for digital infrastructure, and partly by the recognition that Earth's rotation is no longer drifting in a predictable, consistently slow direction. The planet is oscillating. Managing that oscillation with 1-second interventions is increasingly impractical. The retirement of the leap second is a technical administrative matter, but it illustrates something about the relationship between Earth and the systems humans have built on it. We have been tracking the planet's rotation for decades, with instruments precise enough to catch millisecond deviations. We have been managing the gap with occasional corrections, and now the planet is doing something different enough from the long-term trend that the management system itself has had to be rethought. To understand what is happening in that deep interior, though, you first have to understand how we know anything about it at all, because no instrument has ever touched it. The deepest hole ever drilled into Earth's surface is called the Kola Superdeep Borehole. It sits in the Pichengsky district of northwestern Russia, not far from the border with Norway, a small metal cap covering a shaft that plunges straight down into the Kola Peninsula's Archean rock. Soviet scientists began drilling it in 1970 as part of a scientific program to sample the deep crust. They expected the rock to become cooler as they went deeper, following standard geological models of the time. The rock became hotter. By the time the project was terminated in 1994, the borehole had reached a depth of 12.2 kilometers. This is the deepest artificial point ever created on the surface of this planet, and it represents approximately 0.2% of the distance to Earth's center, less than 1/5 of 1%. The drill stopped not because the program ran out of ambition, but because the temperature at that depth exceeded 180 degrees Celsius, far beyond what the drill equipment could handle. The rock itself was so hot that it behaved more like plastic than hard stone. The inner core is 6,371 kilometers from the surface. It sits beneath 30 kilometers of crust, then roughly 890 kilometers of dense silicate rock called the mantle, then 260 kilometers of liquid iron alloy in the outer core, and only then, at the planet's absolute center, the solid iron sphere. There is no technology that exists, or that could reasonably be engineered, to penetrate all of that. The pressure at the inner core boundary reaches 3 million times Earth's atmospheric pressure. The temperature approaches 5,400 degrees Celsius, roughly comparable to the surface of the Sun. The iron of the inner core is solid, not because it is cool, which it is not, but because it is under such extreme compression that the atoms simply cannot arrange themselves into a liquid state regardless of the temperature. Everything science knows about the inner core comes from a single indirect method: earthquakes. When a large earthquake occurs somewhere on Earth's surface, it sends seismic waves outward in all directions, waves that travel through the rock and metal and liquid iron of the planet's interior. These waves move at speeds that depend on the properties of the material they pass through. Dense solid rock transmits them faster than loose material. Liquid iron transmits them differently than solid iron. When a wave crosses from one material into another, it bends, changes speed, and sometimes partially reflects back. By detecting these waves at seismic stations on the other side of the planet, measuring their arrival times with extreme precision, and comparing those measurements to models of what the waves should look like if the interior were composed of specific materials at specific depths, seismologists can infer the structure of a planet. They will never be able to directly sample. A comparison to medical ultrasound is close but not exact. In an ultrasound scan, you send waves in and read the echoes. In seismic imaging, you wait for the planet to generate its own waves through earthquakes, then read the signals that emerge at distant stations. You do not control the source. You work with what the planet provides, but the principle is similar. Waves carry information about the interior they pass through, and skilled interpretation of that information reveals structure. Inge Lehmann, a Danish seismologist working in Copenhagen in 1936, used this method to discover something that no one had seen. She was analyzing the records from a major earthquake in New Zealand, tracking the seismic waves as they arrived at stations in Europe, and she noticed that certain waves were showing up in places and at times they should not have appeared. given the then current model of Earth's interior as a liquid metal core enclosed in solid rock. The data did not fit. Rather than dismissing the anomaly, she proposed an explanation. Inside the liquid metal region, there was a solid sphere, denser than the surrounding liquid, that was deflecting waves in ways the existing model could not account for. She was proposing the existence of Earth's inner core based entirely on the pattern of wave arrivals at surface stations. She was right. The inner core she inferred from seismic anomalies in 1936 is the same inner core that later, more sophisticated studies have been mapping ever since. Her insight, made at a desk in Copenhagen with paper records, established the foundation of everything we now know about what sits at the center of this planet. What is being built on that foundation, over the following 9 decades of increasingly precise seismic monitoring, is a detailed enough picture of the inner core's properties that scientists can now detect not just its existence, but its rotation, specifically whether it is rotating at the same speed as the surface above it, faster or slower. And what the latest data says about that question settled, in 2024, a debate that had been running for 20 years. But understanding how seismic data has become precise enough to detect something as subtle as the inner core's rotation rate requires understanding the global seismic network itself and how it accumulated the data that made the 2024 result possible. The modern global seismic network consists of several hundred permanent seismic stations distributed across the planet's surface, supplemented by hundreds of additional regional and temporary networks. Each station contains a seismometer, an instrument that detects ground motion with extraordinary sensitivity. Modern broadband seismometers can detect ground motion of less than a nanometer, 1/1000th of a meter, and can record the full range of seismic wave frequencies, from the long-period oscillations of Earth's normal modes that ring for days after a major earthquake, to the short-period body waves that travel through the interior at high velocity. These stations are connected to data centers that archive, synchronize, and distribute their records in near real time. The Incorporated Research Institutions for Seismology in the United States, the International Seismological Center in the United Kingdom, and similar organizations around the world maintain the global archives that allow researchers to access earthquake records going back decades for the most important stations. The key to studying inner core rotation is the concept of repeating earthquakes or multiplets. When 2 earthquakes occur in the same location, weeks or years apart, and produce similar waveforms, those waveforms should be nearly identical at any given seismic station, assuming nothing along the path between the source and the station has changed. If anything along the path has changed, specifically if the inner core has rotated into a slightly different position since the first earthquake, the waveforms will differ in a predictable way. The difference will be small, but with enough earthquake pairs and enough data quality, it can be measured. The challenge is finding enough high-quality repeating earthquakes to build a statistically robust picture. The seismic record goes back to the early 20th century for the oldest stations, but the network was sparse until the 1960s when improvements in seismic instrumentation and recording technology, combined with the monitoring requirements of the Cold War nuclear test ban treaties, led to a major expansion of global seismic monitoring. The dataset available for studies of inner core rotation is, in practical terms, primarily from 1964 onward, when modern seismic recording became widespread. Over 60 years of this dataset accumulated patiently by hundreds of stations across the globe, the 2024 paper had enough earthquake pairs to track the inner core's rotational position year by year, documenting the forward phase from 2003 to 2008 and the backward phase from 2010 onward, with enough precision to close the debate. The 60 years of data were not sufficient in 1984 or 1994 or even 2004. They became sufficient only when enough earthquake pairs had accumulated, and when the analytical methods for extracting the rotation signal from the seismic noise had been refined enough to use them. This is the pace of discovery at the frontier of deep Earth geophysics. Not sudden revelation, but slow accumulation. Decades of instruments, decades of earthquakes, decades of data, until the picture becomes clear enough to say something definitive. The question of whether the inner core rotates independently of the rest of Earth was first raised seriously in the 1990s, when seismologists began noticing subtle but consistent variations in the travel times of seismic waves that had passed through the inner core along similar paths. The waves were arriving at slightly different times depending on which direction they traveled through the core. This anisotropy, as it is technically called, was most likely caused by the inner core's iron crystals being aligned in a preferred direction, and if that alignment was caused by the core's rotation being slightly different from the mantle's rotation, then tracking how the anisotropy changed over time would reveal something about the rotation itself. A paper published in 1996 by Xiaodong Song and Paul Richards suggested that the inner core was super-rotating, spinning about 1 degree per year faster than the mantle. This would cause the anisotropy pattern to shift over time as the core rotated beneath the mantle, and measurements of repeating earthquakes, pairs of earthquakes in the same location at different times, whose seismic waves traveled through the same paths, showed exactly this kind of shift. Other researchers disagreed. Different data sets, different earthquake pairs, different analysis methods produced different estimates. Some studies found slower superrotation. Some found near-zero differential rotation. Some found evidence of oscillation. The debate became one of the most contested in deep Earth geophysics, with competing groups publishing conflicting results for 2 decades. The technical difficulties were real. Seismic waves passing through the inner core travel different distances and at different angles depending on the source and receiver locations. The inner core is not seismically uniform, and separating the signal of rotation from the background of structural heterogeneity requires careful analysis. Different researchers made different assumptions about how to handle this background, and different assumptions produced different results. Some studies used only a handful of earthquake pairs. Others used hundreds. Some focused on specific geographic corridors where the seismic paths were particularly informative. Others used global data sets. The debate was also complicated by the question of what standard to measure rotation against. The inner core's rotation rate is always measured relative to something, and the choice of reference frame matters. Most studies use the mantle as the reference, asking whether the inner core rotated faster or slower than the rock immediately above the outer core. But the mantle itself is not perfectly rigid. It has a slight viscoelastic character and can respond to the forces imposed on it by the outer core and the inner core over long timescales. Choosing a reference frame for rotation in a coupled, deforming system is a subtler problem than it first appears. What the debate lacked was a large enough collection of high-quality repeating earthquake pairs spanning a long enough time period, analysed with methods rigorous enough to unambiguously separate the rotation signal from other sources of wave variation. The 2024 paper published in Nature by Wei Wang, John Vidali and colleagues at institutions including the University of Southern California, the Chinese Academy of Sciences, Cornell University and the University of Utah, addressed this problem directly. The team compiled a collection of seismic data spanning from 1964 to 2021 and identified a large set of what they called multiplets, groups of earthquakes in the same location whose waveforms closely matched each other. By tracking how the waveforms evolved across pairs of earthquakes separated by years, they were able to document not just whether the core was rotating, but how the rotation rate had changed over time. The picture that emerged was specific and, in some ways, unexpected. From roughly 2003 to 2008, the inner core was super-rotating, moving slightly faster than the mantle. Then, beginning around 2008 and becoming clear by 2010, the super-rotation slowed. The inner core's rotation rate converged with the mantle's and then went past it. Since approximately 2010, the inner core has been sub-rotating, moving at a rate slightly slower than the mantle. When something moves slower than the reference frame surrounding it, it appears, relative to that reference frame, to be moving backward. The inner core is not spinning in reverse in any absolute sense. Earth is not turning inside out. What is happening is that the solid iron sphere at the planet's center has slowed its rotation below the rate of the mantle and crust above it, and that relative slowing, by the conventions of how rotation is measured in a reference frame tied to the surface, looks like backward motion. The difference in rate is tiny. The angular difference accumulates slowly, but is real. It is consistent with the data, and it closes a debate that ran for nearly 3 decades. John Vidali, one of the study's authors, described the confirmation this way. "We have been arguing about this for 20 years, and I think this nails it. What the reversal tells us is not just that the inner core is moving at a different rate from the surface, It tells us that the forces acting on the inner core have changed. The inner core's rotation rate is determined by the balance of forces it experiences: electromagnetic coupling from the outer core's magnetic field, gravitational coupling from the mantle above, and the pressure torque exerted by the topography of the inner core's surface. If those forces have shifted enough to take a core that was super-rotating and turn it into one that is sub-rotating, something has changed in the system of forces operating at that depth. Something in the way the outer core is flowing, or the way the mantle is coupling to the core, or both, has evolved over the past 2 decades in a way that altered the rotational balance of the innermost sphere. Then, 3 months later, the same team published something harder to explain. The 2025 paper appeared in Nature Geoscience in February, less than a year after the rotation reversal paper. It used much of the same seismic dataset, the same collection of repeating earthquakes and carefully matched waveforms, but it asked a different question. Not where has the inner core rotated to, but has the inner core changed shape? The observation that prompted the question was specific. When the team looked at how seismic wave amplitudes, the height of the waves rather than their arrival time, had varied across different earthquake pairs and different seismic stations, they found a pattern that could not be explained by rotation alone. 2 stations in northern Canada, one at Yellowknife in the Northwest Territories and one at Fairbanks in Alaska, were receiving waves from the same earthquake sources along similar paths. If the only thing changing about the inner core were its rotational position, both stations should have seen similar patterns of amplitude variation over time. They did not. Yellowknife showed systematic changes that were not mirrored at Fairbanks. The discrepancy was too organized to be random noise. It was too consistent across different earthquake pairs to be explained by local geology at either station. The most physically coherent interpretation, the one that best fit the data when multiple alternative explanations were tested, was that the surface of the inner core was changing, not just rotating through different positions, but physically deforming. Material rising in some places, sinking in others, altering the topography of the boundary between the solid inner core and the liquid outer core that surrounds it. John Vidale, the lead author of this second study, described the inference in terms that scientists rarely use when discussing geological data. He said, "It is almost science fiction to imagine what is happening on the surface of the inner core. Perhaps the topography is rising and falling. The phrase is carefully chosen. Vidale is not describing imagination. He is describing inference, the product of applying physical models to seismic data." But the qualifier almost science fiction is honest about how far the result is from anything that has been directly observed. A boundary between solid and liquid iron, 5,150 kilometers below the surface, under 3 million atmospheres of pressure, at temperatures approaching 5,400 degrees Celsius, is changing its shape on timescales of years to decades. The landscape at the center of the planet is, in a slow and extreme sense, moving. The physics of how this happens is not yet resolved. The standard models of iron behavior under inner core conditions, which treat the deep interior as uniform and rigid, do not easily accommodate surface deformation of this kind. Some researchers have proposed that the outer layers of the inner core close to the boundary with the outer core may have different physical properties from the deeper interior, perhaps a degree of structural softness or heterogeneity that allows slow deformation under the stresses imposed by the outer core's flowing liquid. The 2025 paper establishes the observation. The mechanism remains an open question for future research to address. What the 2 papers together have done is transform the picture of the inner core from a static, uniform, rigidly rotating sphere into something considerably more dynamic. The inner core has reversed its relative rotation direction. Its surface is deforming. Both of these changes involve forces that connect the inner core to the outer core above it, and the outer core is where Earth's magnetic field is generated. But before moving to the outer core and the magnetic field, it is worth sitting with what the deformation finding actually implies about the inner core's physical state. The standard picture of the inner core, which prevailed until recently, treated it as a homogeneous solid sphere of iron and nickel, behaving rigidly under the extreme pressure at its center. This picture was always a simplification. Seismic studies over the past few decades have revealed that the inner core is not homogeneous. It shows different seismic velocities in different directions, suggesting that iron crystals inside it are not randomly oriented, but aligned in a preferred direction, probably set by the pattern of convective flow in the outer core during the inner core solidification. It shows what some researchers describe as an inner core, a distinct region at its very center that may have different crystalline structure from the outer part of the solid sphere. The possibility that the outer layer of the inner core, the part nearest the inner outer core boundary, has different physical properties from the deeper interior has been discussed in the literature for some years. Iron at these conditions, extremely high pressure and temperature simultaneously, can exist in multiple crystalline phases. The transition between phases can change the mechanical properties of the material, including its resistance to deformation. If the outermost layer of the inner core is in a crystalline phase that is slightly softer or more heterogeneous than the deeper interior, then slow topographic deformation at the surface of the inner core becomes physically plausible, even under conditions that would otherwise make any deformation of solid iron seem impossible. This is the theoretical framework within which the 2025 observation fits most naturally. The inner core's surface is not a perfectly smooth, rigidly fixed boundary. It is a boundary between solid and liquid iron under extreme conditions, and the exact conditions at that boundary, the temperature gradient, the pressure, the composition of the liquid above, and the crystalline phase of the solid below, may allow for slow changes in topography that are large enough to produce detectable seismic signals over decades. Whether this interpretation is fully correct will require more data and more modeling. But the observation stands independently of the mechanism. The two seismic stations in Canada recorded different things, consistently, across earthquake pairs spanning more than 3 decades. Something changed along the path between the earthquake sources and those stations, and that something is almost certainly at the inner core boundary. The inference of topographic deformation is the best current explanation. The magnetic field does not come from a magnet. This is the first thing most people need to unlearn when they start to understand Earth's field seriously. The intuition from classroom education is of a bar magnet buried somewhere inside the planet, fixed in orientation, pointing persistently north. This model works well enough to explain compass behavior. It fails completely to explain how the field actually works, why it changes over time, why the magnetic north pole moves, why the field varies in strength in different parts of the world, and why it has reversed its polarity hundreds of times over Earth's geological history. The reality is not a magnet, it is a process. Earth's outer core is a shell of liquid iron and nickel, roughly 2,260 kilometers thick, sitting between the solid inner core below and the rocky mantle above. Its temperature ranges from approximately 4,000 degrees Celsius at the outer boundary, where it meets the base of the mantle, to approximately 5,400 degrees at the inner boundary, where it meets the solid inner core. The temperature difference between these two surfaces, combined with compositional differences as lighter elements are released by the ongoing solidification of the inner core, drives convection. Hotter, lighter material near the inner core boundary rises. Cooler, heavier material near the mantle boundary sinks. Earth's own rotation causes these rising and sinking columns of liquid metal to twist, aligning them in organized structures parallel to the planet's rotation axis. Moving liquid metal conducts electricity. A conductor moving through a magnetic field generates an electric current, and electric currents generate magnetic fields. The convective columns in the outer core generate electric currents, which generate magnetic field lines. But the field does not simply add to itself and grow without limit. The field itself exerts forces on the conducting fluid, guiding the currents that generated it, reshaping the convective pattern. The whole system is self-regulating. The fluid motion produces the field. The field influences the fluid motion. The influenced fluid motion sustains and shapes the field in a continuous feedback loop. This is the geodynamo. A useful analogy, though imperfect, is the bicycle dynamo, the small generator that attaches to a wheel and converts rotation into electricity for a lamp. In a bicycle dynamo, a permanent magnet rotates near a wire coil, and the changing magnetic field through the coil drives a current. The geodynamo works through a conceptually related but far more complex version of the same electromagnetic induction principle. Moving conducting fluid through magnetic field lines generates current, which reinforces the field, which organizes the fluid flow, which maintains the current. The bicycle dynamo has a permanent magnet to initiate the process. The G-dynamo sustains itself through the feedback between field and fluid. If the convection in the outer core were to stop, the field would decay, not immediately but over a timescale of roughly 1 to 10,000 years, as the existing field dissipated without the convective currents to sustain it. The planet would gradually lose its magnetic shield. The solar wind would interact more directly with the upper atmosphere. The long-term consequences would be significant. This is not a scenario expected by any current model of Earth's interior, given the ongoing heat flow from the cooling inner core that drives the convection, but it is the physical consequence that makes the G-dynamo worth understanding. Everything it does depends on that continuous circulation of liquid iron, 3,000 kilometers down, running every second of every day. The structure of the convection in the outer core is not random turbulence, it is organized. Earth's rotation imposes order on the fluid, a phenomenon described by a principle in geophysical fluid dynamics called the Taylor-Proudman theorem. In a rapidly rotating fluid, motion tends to become organized in columns aligned with the rotation axis. The convective currents in the outer core are not simply rising and sinking blobs of liquid metal. They are organized columns aligned with Earth's spin axis running roughly north to south through the liquid shell. These columns rotate slowly around the inner core, generating the electric currents that power the G-dynamo. The geometry of the outer currents matters for the structure of the field it produces. The tangent cylinder, an imaginary cylinder aligned with Earth's rotation axis and tangent to the inner core at its equator, divides the outer core into two regions: the region inside the tangent cylinder, which is more directly influenced by the inner core, and the region outside it. The large-scale convective columns tend to operate outside the tangent cylinder. Inside the tangent cylinder, close to the inner core, the dynamics are different and more directly connected to what is happening at the inner core boundary. This geometry is one reason why changes at the inner core boundary, the kind documented in the 2024 and 2025 papers, are expected to influence the magnetic field structure. The inner core directly affects the dynamics inside the tangent cylinder, and those dynamics feed into the overall convective pattern of the outer core. The G-dynamo is a coupled system from its innermost boundary to its outer edge, and a change at the center propagates, over time, to the field it produces. The field produced by the G-dynamo extends far beyond Earth's surface. Field lines emerge from the core, pass through the mantle and crust, continue through the atmosphere, and stretch into space. On the sunward side, the pressure of the solar wind compresses the magnetosphere, the region of space dominated by Earth's field, to a distance of roughly 60,000 kilometers. On the night side, the solar wind stretches the magnetosphere into a long tail, extending hundreds of thousands of kilometers behind the planet. The magnetosphere deflects the constant stream of charged particles in the solar wind, most of the time routing them around Earth rather than through it. The word deflects is worth being specific about. The solar wind is not merely a stream of light. It is a flow of charged particles, mostly protons and electrons, moving at several hundred kilometers per second and carrying a significant energy flux. When these particles encounter Earth's magnetosphere, most of them are rerouted around the planet, guided by the field lines away from the surface. Some are captured and channeled toward the poles, where they enter the upper atmosphere and produce auroras. A small fraction penetrates the magnetosphere and reaches the inner radiation belts. The vast majority never reaches the surface. The aurora is perhaps the most visible reminder, for those who live at high latitudes, that the magnetic field is not an abstraction. When charged particles from a solar storm hit Earth's magnetosphere and funnel down field lines toward the polar regions, they collide with atmospheric gases at altitudes of roughly 100 to 300 kilometers. The collisions excite the gas atoms, and as the atoms return to their ground state, they emit light, green from oxygen at lower altitudes, red from oxygen at higher altitudes, blue and purple from nitrogen. The aurora is the sound of the magnetosphere doing its job, made visible. During strong solar storms, auroras can be seen as far south as the tropics. Mars has no global magnetic field. It has patchy crustal remnants, localized magnetic signatures preserved in ancient rock from the time when the Martian dynamo was still operating, billions of years ago. These remnants are not strong enough to shield the surface. the solar wind hits the Martian upper atmosphere directly. Mars has no auroras produced by functioning magnetosphere because it has no functioning magnetosphere to produce them. Everything alive on this planet exists, in some meaningful sense, because liquid iron is circulating in organized columns 3,000 kilometers below the surface right now, sustaining a field that has been deflecting the solar wind for most of Earth's history. The G-dynamo is not a geological curiosity. It is one of the conditions of habitability on this planet, and its behavior, measured over the last decade with tools that didn't exist 2 decades ago, is changing. In 1831, a British naval officer named James Clark Ross stood on the Boothia Peninsula in what is now northern Canada and planted a flag. He was not planting a flag to claim territory. He was marking the location of something that had been sought by navigators for centuries, the magnetic North Pole, the point on Earth's surface where a compass needle dips straight down rather than pointing horizontally toward the horizon. He had found it. He confirmed the position with instruments. He recorded the coordinates. He sailed back to report. That position is now approximately 2,300 kilometers from where magnetic north currently sits. The pole Ross found in 1831 was not a permanent feature of the landscape. It was the surface expression of a particular pattern in the liquid outer core beneath that region, a cluster of magnetic field lines converging and emerging from the core in a way that produced a local concentration of northward field. When the convective pattern in the outer core shifts over time, that cluster shifts with it. The pole is not anchored to any geographic feature. It follows the internal dynamics of the G-dynamo, drifting where the dominant flux lobe directs it. For most of the period between 1831 and the late 20th century, the drift was manageable. The pole moved roughly 10 to 15 kilometers per year across the Canadian Arctic, a rate that navigators and cartographers could account for with periodic recalibrations of their charts. Slow enough to be nearly static on any practical timescale. Then, in the 1990s, the drift accelerated. By the 2010s, it had reached roughly 50 kilometers per year, more than 3 times the historical average, moving consistently in the same direction northward across the Arctic Ocean, away from Canada towards Siberia. In January 2019, the World Magnetic Model, the global navigational reference, jointly maintained by the National Oceanic and Atmospheric Administration in the United States and the British Geological Survey, required an emergency update. The model had been scheduled for its regular 5-year revision in December 2019. The early release was triggered by a single finding. The pole had moved faster than the model's forecast could accommodate, and the model had drifted outside its acceptable accuracy margin. Navigation systems that depend on the model had to be updated ahead of schedule to correct for a pole position the model had failed to predict. The January 2025 update, which followed the normal cycle, confirmed the accuracy of the subsequent forecast. The pole was where scientists had predicted it would be. The system was working, but what the 2019 episode demonstrated clearly was the edge of the system's predictive capacity. Even the best available model built by the world's leading geomagnetists with the most precise satellite data in history had failed to forecast the pole's movement over a 5-year window. Understanding why the pole is moving requires understanding the structure underneath it. The European Space Agency launched the Swarm satellite constellation in November 2013. 3 satellites designated Alpha, Bravo, and Charlie were placed in precisely calibrated orbits designed to separate the magnetic signals coming from different sources: the core, the mantle, the crust, the oceans, and the ionosphere. Over the following years, the swarm data built the most detailed and continuously updated picture of Earth's magnetic field ever assembled. A study published in early 2026, drawing on the full 11-year swarm dataset, documented what had happened to the field's internal structure between 2014 and 2025. The findings were specific. The magnetic field over northern Canada had weakened. A region of concentrated field, one of the 2 main flux lobes that determine where the magnetic North Pole sits, had shrunk by an area comparable to the country of India. Meanwhile, the corresponding flux lobe beneath Siberia had strengthened, growing by an area comparable to Greenland. The pole was following the shift as the Canadian lobe weakened and the Siberian lobe strengthened. the surface expression of the dominant flux concentration migrated northward and westward. The flux load changes are driven by processes in the outer core, in the flows of liquid iron thousands of kilometers below the surface. Exactly which changes in outer core flow are responsible, and why those flows have shifted in this particular way over this particular time scale, is a research question that has not yet been fully resolved. What the swarm data does is document the magnetic consequence of those changes with a precision that allows the pole's movement to be tracked and, within limits, predicted. The practical consequences of the pole's movement reach into every navigation system on the planet. Aircraft autopilots use magnetic heading as one of their orientation references. GPS devices cross-reference satellite positioning with the World Magnetic Model to convert raw coordinates into usable directional information. Airport runways are designated by their magnetic compass bearing, and runway designations must be updated when the local magnetic declination, the angle between magnetic and geographic north, shifts enough to change the bearing by more than 5 degrees. In recent years, airports in parts of Alaska and Russia have updated their runway designations specifically because of the pole's movement. None of this is a crisis. Navigation systems have always required periodic recalibration. What the current acceleration represents is a faster rate of recalibration than the system was designed to handle under normal conditions. The infrastructure is adapting, but the need to adapt more frequently than historical norms suggests is itself a measurement. The field is changing faster than the baseline period on which the infrastructure was designed. There is a historical parallel worth mentioning, not for dramatic comparison but for perspective. In the era before GPS, when ships navigated primarily by magnetic compass, the drift of the magnetic pole was a slower and less urgent problem. Navigators corrected for magnetic declination, the angle between magnetic north and geographic north at their location, using charts that were updated periodically. The charts were accurate enough for the ships of their time, but the time scale of change was manageable. In the modern era, the dependency on magnetic field accuracy is far deeper. Magnetic navigation is embedded in systems that update themselves continuously, that depend on the World Magnetic Model as a background reference for everything from a smartphone compass to an aircraft's flight management computer. When the field changes faster than the model, the entire layer of technology built on top of it experiences a growing inaccuracy that must be corrected at scale. The 2019 emergency update was not a dramatic event, but it was a signal. The rate of change in the field has exceeded the rate at which the infrastructure built around it was designed to track that change. The system adapted. It will need to adapt again, and possibly again after that, if the pole continues its current trajectory towards Siberia at its current speed. There is a region of the Atlantic Ocean, roughly centered southeast of South America and extending across the southern portion of the ocean toward Africa, where Earth's magnetic field is significantly weaker than anywhere else on the planet. The South Atlantic Anomaly, as it is called, was first identified in the 19th century when ships crossing that part of the ocean noticed irregularities in their compass readings. It has been monitored more closely as instruments improved. What the monitoring revealed over the course of the 20th century is that the anomaly is not static. It is moving, generally westward. And it is growing. The 11 years of swarm satellite data analyzed in the 2026 study documented the growth in detail. Between 2014 and 2025, the anomaly expanded steadily. The region of lowest field strength, the core of the weak zone, shifted position. A secondary minimum appeared to the southwest of the original center, suggesting the anomaly may be developing a bifurcated structure, 2 weakness zones rather than 1. The total area of the anomaly, defined by a field strength threshold, increased, and the changes in the anomaly are consistent with the same flux lobe dynamics that are driving the pole's movement. As the Canadian flux lobe weakens, the field it generates in the southern hemisphere weakens too. And the South Atlantic Anomaly, which sits in the region most affected by the Canadian lobe's influence, expands. The anomaly matters practically because of what a weak magnetic field means for objects in orbit. Earth's magnetic field normally deflects the energetic charged particles in the solar wind and cosmic ray background, routing them around the planet. In the South Atlantic Anomaly, where the field is weaker, this deflection is less effective. Particles that would be deflected away at other longitudes penetrate more deeply, reaching the orbital altitudes used by low Earth orbit satellites. The International Space Station, which occupies a low Earth orbit at an inclination that takes it through the anomaly region repeatedly, is exposed to elevated radiation levels during each pass. Sensitive instruments aboard the station and aboard other satellites that cross the anomaly are routinely put into protective modes when their orbit takes them through the weak zone. The Hubble Space Telescope has experienced this directly. Certain of its scientific instruments were shut down during anomaly passes for years because the elevated radiation environment during those passes caused data quality problems that outweighed the scientific value of attempting observations. Other satellites in the region have experienced single-event upsets, transient hardware malfunctions caused by energetic particles striking electronics. Most of these events are recoverable. Some have caused permanent component damage. The growth of the anomaly means that a larger portion of each orbit is spent in the elevated radiation zone. For any satellite crossing it, the radiation dose accumulated per pass increases as the anomaly expands. The long-term planning of satellite missions in low Earth orbit must now account for an anomaly that is somewhat larger than it was when the mission was designed. The growth is slow enough that it does not threaten any currently operational satellite over its designed lifespan, but it is fast enough to be a factor in the next generation of mission planning. There is a dimension of the anomaly's consequence that extends beyond the engineering of individual satellites. The global communications and navigation infrastructure that humanity depends on is largely carried by satellites in low and medium Earth orbit, weather forecasting satellites, environmental monitoring satellites, military reconnaissance satellites, commercial imaging satellites, and the GPS and Galileo navigation constellations all operate in environments that are affected to varying degrees by the magnetic field. As the anomaly grows, the radiation environment in a larger portion of orbital space becomes elevated. The aggregate effect on the entire constellation of operational satellites is an increase in the long-term radiation dose and in the frequency of single-event upsets, the transient hardware faults caused by energetic particles striking semiconductor circuitry. Most of these effects are manageable with current satellite design standards. Satellites bound for orbits that cross the anomaly are designed with radiation-hardened electronics and additional shielding. Operational procedures account for the passes through the weak zone, but the margins are not infinite. As the anomaly expands, the engineering assumptions that went into satellites designed a decade ago may become inadequate sooner than their originally planned operational lifetimes. This is not a current crisis. It is a factor in the long-term planning of the infrastructure that runs on the magnetic environment. The physical cause of the anomaly at the level of the outer core involves a reversed polarity patch in the geomagnetic field. The outer core does not produce a perfectly uniform field. In the chaotic turbulence of the fluid dynamo, localized regions develop where the magnetic field points in the opposite direction from the dominant global field, where the main field emerges northward from the core and bends around the planet in a systematic way. These reversed patches locally cancel part of the main field, reducing the net field strength at the surface above them. The South Atlantic Anomaly sits above one such reversed patch. The fact that it is growing suggests the reversed patch is growing, or that the main field in that region is weakening relative to the reversed patch, or both. The swarm data constrains this picture. The details of the outer core dynamics that are driving it remain an active research question. What the anomaly and the pole movement together illustrate is a field in flux, not in crisis, not reversing tomorrow, but shifting in organized ways that track with changes in the outer core's internal structure, changes that are now being monitored in something close to real time by instruments that have only been in orbit for a decade. The inner core has reversed its relative rotation direction, its surface is deforming. The outer core's convective pattern is shifting, producing a moving magnetic pole and an expanding weak zone in the southern hemisphere. Earth's rotation speed is fluctuating in ways that surface processes alone cannot fully account for. These are 4 separately measured observations. The question this chapter asks is whether they are part of the same story. The honest answer is possibly. Possibly is a carefully chosen word here. It is not a hedge toward ignorance. It reflects the specific state of current scientific knowledge about a system whose causal pathways are established in principle but not confirmed in detail for the current situation. The physical connections between Earth's internal layers are real and well established. The inner core does not sit in isolation. It shares its boundary with a liquid outer core, and across that boundary, several forms of energy and momentum are continuously exchanged. Heat flows outward from the inner core into the liquid above it, driving the convective circulation that powers the G-dynamo. As the inner core solidifies at its surface, it releases lighter elements into the liquid outer core, which adds buoyancy to the base of the convective columns and intensifies the circulation. Angular momentum is exchanged across the boundary through electromagnetic coupling and through the mechanical pressure that the inner core's topography exerts on the liquid flowing past it. This last mechanism, topographic coupling, is directly relevant to what the 2025 paper described. If the inner core surface topography is changing, as the seismic evidence suggests, the pressure distribution at the inner core boundary changes with it. Different topographic shapes impose different forces on the overlying liquid. Those forces alter the convective pattern of the outer core in ways that can, over time, change the magnetic field output of the geodynamo. The causal chain from inner core surface deformation to outer core flow change to magnetic field change is physically coherent. Whether the deformations currently inferred from seismic data are large enough and fast enough to be producing the observed changes in the magnetic field is the question that current models cannot yet answer. The rotation connection runs through a related mechanism. Changes in the flow of the liquid outer core, driven by the convective pattern of the geodynamo, are transmitted to the solid mantle above through electromagnetic coupling. The outer core's magnetic field threads through the conducting lower mantle, and as the field changes, it exerts torques on the mantle. Those torques can accelerate or decelerate the mantle's rotation, and since the crust rides the mantle, they affect the length of the day. The coupling between outer core flow and surface rotation through electromagnetic interaction is established in geophysical literature and is the primary candidate mechanism for explaining multi-decadal variations in Earth's rotation that surface processes alone cannot account for. The simultaneous occurrence of inner core reversal, inner core surface deformation, magnetic pole acceleration, South Atlantic anomaly growth, and rotation speed anomalies is therefore consistent with a single underlying shift in the dynamics of the outer core, expressing itself differently across multiple measurement systems. This is the framework most consistent with the available data. It is being studied by multiple research groups using different data sets and different modeling approaches. What it is not is confirmed. The inner core papers and the magnetic field papers were produced by different research teams using different instruments, studying different aspects of the same system. The connection between them is inferred from physical principles, not demonstrated by a single integrated study that models all four phenomena simultaneously and shows they are driven by the same process. That integrated study has not yet been published. It may emerge from ongoing research. It may find that some of the connections are coincidental. It may find stronger connections than the physical principles alone predict. There is a subtlety in the timing worth noting. The inner core's reversal from superrotation to subrotation began around 2010. The acceleration in the magnetic North Pole's movement was already underway by the 1990s, before the inner core reversal became apparent. The South Atlantic Anomaly's recent expansion has been documented from 2014 onward, with the swarm data providing the precise timeline. The Earth rotation acceleration trend became pronounced around 2020. These timescales do not perfectly align, which is itself informative. If all four phenomena are driven by a single shift in outer core dynamics, that shift must be coherent enough to produce related effects on different timescales and in different measurement systems. The fact that the timescales don't perfectly align does not disprove the connection. Different parts of the coupled system respond on different timescales. The electromagnetic coupling between the outer core and the mantle, which is the mechanism connecting outer core flow changes to surface rotation changes, operates on a timescale of decades to centuries. The magnetic field at the surface responds on timescales of years to centuries. The inner core's rotation responds on timescales of years to decades, depending on the coupling mechanism. So a single underlying change in the outer core, happening gradually over several decades, would be expected to express itself in these different measurement systems at different times and at different rates, exactly as observed. This kind of multi-timescale, multi-observable response to a single underlying driver is the signature of a coupled system. It is also harder to confirm than a single simultaneous event would be. The scientific process required to establish the connection will likely take years, involving improved numerical models of the full coupled system, new observational constraints from the swarm mission's extended data record, and a growing library of seismic data on the inner core's behavior. What confirmation would look like, in practical terms, is a numerical simulation of Earth's outer core that can reproduce all 4 observed anomalies simultaneously, starting from a single change in the convective pattern. The computational geodynamics community has been building progressively more realistic models of the outer core for decades. These models have become capable enough to reproduce many features of the observed magnetic field, including the general structure of the field and the broad behavior of the polar wander. They have not yet been able to simultaneously model the inner core's rotation, the outer core's convection, the surface magnetic field, and the Earth's rotation in a single integrated framework, with all the coupling mechanisms included at realistic resolution. That kind of integrated model requires computational resources that are only now becoming available, and a quality of observational constraint that the SWARM mission has over the past decade begun to provide. The convergence of better data and greater computing power is what makes the current moment in deep Earth geophysics particularly active. The questions raised by the 2024 and 2025 papers are not likely to go unanswered for long. They will attract researchers, proposals, and modeling efforts precisely because the data is now good enough to test specific hypotheses rather than merely speculate about possibilities. This is what science at the boundary of what is currently knowable looks like. Not certain, not dismissed. Measured precisely enough to raise the question with confidence, and studied carefully enough that the answer, when it comes, will be real. The current changes, unusual as they are by the baseline of instrumental records, are not the first time Earth's magnetic system has been disrupted. The rock record goes back much farther than any instrument, and what it preserves is a history of repeated, large-scale magnetic upheaval. The mechanism for reading that history is written into the ocean floor. When lava erupts at mid-ocean ridges, the spreading centers where tectonic plates are slowly separating, it cools and solidifies. As the iron-bearing minerals in the new basalt cool through a temperature called the Curie point, the threshold below which magnetic ordering becomes stable, the iron crystals align with the prevailing magnetic field and lock that alignment in place permanently. The rock is a magnetic fossil. It preserves the direction of the field at the moment of its formation. As the ocean floor spreads outward from the ridge over millions of years, these magnetic records spread with it. Looking outward from a mid-ocean ridge, the ocean floor shows alternating bands of rock magnetized in opposite directions. Bands that formed during periods when the magnetic north was in roughly its current position, and bands that formed when it was in the reverse orientation. The pattern is symmetric on both sides of the ridge because the ocean floor spreads equally in both directions from the spreading center. By measuring the age of the rocks and the widths of the magnetic bands, geologists can construct a timeline when the field was in its current normal polarity orientation and when it was reversed. That timeline extends back hundreds of millions of years. What it shows is that reversals are a regular, if irregular, feature of Earth's magnetic history. The field has reversed its polarity hundreds of times. Sometimes the intervals between reversals are long, tens of millions of years. Sometimes they are short, less than 100,000 years. The average over the past few million years is roughly 200,000 to 300,000 years between reversals. The last full reversal, in which magnetic north and south fully exchanged positions, occurred approximately 780,000 years ago. It is called the Brunhes-Matuyama reversal, named for the two geologists whose work helped establish its age and character. Before that reversal, magnetic north was in the southern hemisphere, roughly where magnetic south is today. After it, the field settled into the orientation we experience now. The transition, based on the rock record, took on the order of thousands of years. Between four reversals, the field undergoes shorter disruptions called excursions, events in which the field weakens significantly and the poles shift dramatically without completing a full polarity flip. The Lashams excursion, approximately 41,000 years ago, is the best documented. During this event, the geomagnetic field weakened to roughly 5% of its typical strength. The poles moved far from their usual positions. The reduced field allowed elevated levels of cosmic radiation to reach Earth's surface. Ice cores from Greenland and Antarctica, cave formations called speleothems, and ocean sediment cores all record an increase in cosmogenic isotopes. Isotopes produced when cosmic rays hit the atmosphere during the Larshams period. Modern humans existed during the Larshams excursion. Homo sapiens had been anatomically modern for at least 100,000 years before the excursion occurred, and they survived it. There is no clear evidence in the archaeological or paleontological record of a mass extinction or catastrophic biological disruption associated with the event. The elevated radiation environment was real. The impact on species that depended on the magnetic field for navigation, some migratory birds, certain fish, whales, was likely significant in ways we cannot easily detect at 41,000 years remove. But the field weakening, dramatic as it was, did not end the biosphere. What the Larsham excursion does tell us is that life on Earth has already been through a period of dramatically weakened magnetic shielding and survived it. This is not an argument for complacency about the current decline. It is a calibration point. The field fell to 5% of its normal strength, stayed there for a few centuries, and then recovered. The biosphere survived. Adaptation, migration, and the resilience of ecosystems that had evolved under a magnetic field provided some buffer. The species most affected were probably those that used the field directly for navigation over long distances, and even among those, extinction was not the universal outcome. The current situation, with the field at roughly 85% of its 1840 level, is very far from Larshams conditions. The decline is real and measurable. But between where the field is now and where it was during the Larshams event, lies an enormous amount of further change. Change that the current data does not suggest is imminent. What the Larsham excursion provides is not a warning. It is a reference, evidence of what Earth's magnetic system has done before, and evidence that its worst documented behavior in the past 41,000 years did not produce the catastrophe that the word reversal sometimes implies in popular accounts. The current field strength is measurably declining. From the beginning of systematic instrumental measurement in roughly 1840 to the present, the global average field strength has decreased by approximately 10 to 15%. If this rate of decline continued at its current pace for thousands of years without reversal or recovery, the field would eventually reach Larshams level weakness. But rates of change in geomagnetic systems do not remain constant. The field has weakened and recovered before without triggering a full reversal. Whether the current decline is a prelude to something larger or a fluctuation that will stabilize or reverse is not determinable from the current data. A 2022 study published in Nature Communications examined 9,000 years of geomagnetic field reconstructions and concluded that the current anomalies are within the range of variability seen repeatedly during that period. The South Atlantic Anomaly has appeared in similar forms before. The magnetic North Pole has wandered at similar speeds before. The researchers concluded that the evidence does not support interpreting current conditions as a near-term precursor to a full polarity reversal. That conclusion is specific and careful. It is not a claim that nothing unusual is happening. The current changes are unusual relative to the past century of instrumental records. It is a claim that when the baseline is extended to thousands of years, the unusual becomes less exceptional. The system has done this before. It may be doing it again. Whether it stops here, as it has before, or continues towards something larger, the rocks cannot tell us. Only continued monitoring can narrow the uncertainty. What the rock record can tell us is something about what a reversal actually looks like from the inside, in terms of what the field does during the transition, rather than merely before and after it. The transition between polarity states is not a clean flip, like reversing the direction of a bar magnet. The geodynamo is too complex and too chaotic for that. During the centuries to millennia of a transition, the field weakens significantly, sometimes to a small fraction of its normal strength. The organized dipolar structure, with a clear north and a clear south, breaks down. Multiple poles may appear simultaneously, at different latitudes, wandering unstably. The field becomes complex and irregular, with its structure changing on timescales of decades. Eventually, the convective pattern in the outer core reorganizes around a new dominant configuration, and a stable reversed dipole emerges. With what was magnetic south, now magnetic north. This process is not instantaneous, and it is not uniform across the planet. Paleomagnetic records from different geographic locations show that during past transitions, the field at different points on the globe weakened and recovered at different rates, moved in different directions, and passed through the transition period on somewhat different timescales. The transition was not a single synchronized event experienced everywhere at once. It was a gradual, geographically varied process of one organized state giving way to another. None of the current observations indicate that this process is beginning. The field has been declining for roughly 2 centuries of reliable measurement, and there are signs of more active change in the past few decades, but the decline is within the range of past fluctuations, and the specific conditions that precede a reversal in the paleomagnetic record, particularly a sustained and deep weakening over centuries, have not yet developed. The scientists who study this most carefully are emphatic on this point. Monitoring is warranted, interpretation of the data is ongoing, and the conclusion that a reversal is not imminent is well supported by the available evidence. There is a particular kind of limitation that applies to studying Earth's deep interior, and it is worth being explicit about it rather than leaving it implied. No instrument has ever directly measured the inner core's rotation. No instrument has directly measured the flow patterns of the liquid outer core. No instrument has directly measured the forces exchanged across the core mantle boundary. Everything in the preceding chapters of this script is inferred from surface and near-surface observations. The arrival times and amplitudes of seismic waves, the direction and strength of the magnetic field measured at the surface and from low orbit, the rotation speed of Earth's crust as measured by atomic clocks, GPS satellites, and very long baseline radio interferometry. These methods are powerful. The inferences they support are real and well-founded, but they are inferences, not direct measurements, and they carry the uncertainties inherent in inferring the properties of a hidden system from its surface expressions. This has a direct consequence for prediction. The World Magnetic Model, which represents the best current forecast of where the magnetic pole will be and what the field will look like over the next 5 years, is built from surface and satellite measurements fed into numerical models of the geodynamo. Those models capture the dominant dynamics well enough to produce useful forecasts. They do not capture the full complexity of a turbulent fluid system driven by temperature gradients, compositional convection, Earth's rotation, and the electromagnetic interaction between the fluid and the field it generates. In a chaotic system, small uncertainties in the initial conditions amplify over time. The 5-year forecast horizon of the World Magnetic Model is near the edge of what the current models can reliably produce, as the 2019 emergency update demonstrated. Extending the forecast horizon to decades or centuries is currently beyond the reach of the science, not because the physics is unknown, but because the chaotic character of the geodynamo means that long-range prediction in the usual sense, a specific forecast of where the pole will be in 2075, is not achievable with any methodology currently available. What is achievable is probabilistic characterization. The field is more likely to continue weakening than to immediately strengthen the pole's current trajectory, is more likely to continue towards Siberia than to reverse. A full polarity reversal is more likely to occur on a timescale of thousands of years than on a timescale of centuries. These are not predictions. They are calibrated assessments of a system whose behavior is bounded but not precisely foreseeable. This is not a failure of science. It is a description of the frontier. The geodynamo is a chaotic fluid dynamics problem. Weather forecasting is similarly bounded by the chaotic character of atmospheric fluid dynamics. Yet weather forecasting is practically useful and continues to improve as models are refined and more data is incorporated. Geomagnetic forecasting follows the same path, and the decade of swarm data has produced improvements in both model accuracy and understanding that were not achievable before 2013. The analogy between weather forecasting and geomagnetic forecasting is instructive in another way. In the 1950s, weather forecasting was a largely empirical art, based on pattern recognition in historical records. The fundamental physics of atmospheric dynamics was understood, but the computational power to apply that physics to quantitative forecasts did not exist at the necessary resolution. By the 1990s, numerical weather prediction models running on supercomputers had transformed the field. 7-day forecasts that were barely better than chance in the 1960s became reliable enough to plan operations around. The improvement came from 3 sources: better observations from satellites and weather stations, better computational models, and better physical understanding of the processes at work. Geomagnetic forecasting is in an analogous earlier stage. The fundamental physics of the G-dynamo is well enough understood that researchers can write down the governing equations. The computational power to solve those equations in 3-dimensional models of Earth's outer core now exists. The observations from the SWARM mission and from the global network of ground-based magnetic observatories are improving. The model skill is improving. The process is slower than it was for weather, because the G-dynamo operates on longer timescales and the observational record is shorter. But the direction is the same. The instruments continue to run. The SWARM satellites, still operational, are extending their dataset into a second decade of continuous magnetic field monitoring. The global seismic network is adding to its collection of repeating earthquake pairs every year, building the dataset that future studies of inner core rotation and deformation will draw on. The atomic clocks are counting. Each year that passes without a major disruption to any of these systems adds more data to the picture and narrows the range of models consistent with observation. There is something worth noting about the pace at which understanding has advanced. The inner core's existence was inferred from earthquake records in 1936. The possibility that it rotates independently from the mantle was first proposed in the 1990s. The debate over the direction and speed of that rotation ran for nearly 30 years before the 2024 paper resolved it. The possibility that the inner core surface is deforming was unthinkable before the precision of the current seismic dataset made it visible. Each step required not just better ideas but better data, accumulated over longer baselines, analyzed with methods that only became available as computational power increased and as the global seismic network expanded and improved. The same pattern applies to the magnetic field. The SWARM satellite constellation, launched in 2013, produces more data about the field's 3-dimensional structure in a single month than the entire preceding century of surface observations combined. The models built on that data are better than any that came before, not because the physics changed, but because the observational constraint tightened enormously. The emergency update in 2019 was possible only because the model had been built to a standard of accuracy that made the discrepancy visible. A less accurate model would not have detected that the pole had moved outside its predicted range. What is happening to Earth right now will be better understood in 10 years than it is today. In 20 years, better still, the planet does not wait for understanding. It simply continues doing what it has been doing for 4.5 billion years, and the instruments we have placed on and around it keep watching. Let's go back to the beginning. Not to the beginning of this script, to the beginning of the planet. 4.5 billion years ago, Earth formed from the collision and accretion of smaller bodies in the early solar system. The energy of those collisions melted the entire planet. Over the first several 100 million years, heavy iron sank toward the center, while lighter silicate rock rose toward the surface. The core differentiated from the mantle. The outer core formed as a liquid. The inner core began to nucleate at the center, solidifying under the extreme pressure even at the temperatures present there. Estimates of when the solid inner core first formed range from roughly 1 billion years ago to as recently as 500 million years ago, with some studies suggesting even younger formation. The inner core is, in geological terms, possibly one of the youngest major features of the planet. It is still growing, adding to its radius by perhaps a millimeter per year as the outer core slowly cools and more liquid iron crosses the boundary into solidity. The inner core we are studying today is not the same inner core that was present when the dinosaurs were alive. It is measurably larger. Every millimeter of inner core growth releases latent heat into the outer core and releases lighter elements that add buoyancy to the base of the convective columns. The inner core's growth is part of what sustains the G-dynamo. As the inner core grows, it feeds the circulation that produces the magnetic field. The geodynamo is powered, in part, by the planet's own gradual cooling from the inside out. The magnetic field has been operating for most of Earth's history. Evidence from ancient rocks in southern Africa and Australia suggests the field was present at least 3.5 billion years ago. It has been reversing ever since, hundreds of times, with no fixed schedule and no obvious pattern that would allow a prediction of when the next reversal will come. The field has not failed. It has fluctuated within the wide range of behavior characteristic of a chaotic self-sustaining dynamo. There is something worth pausing on in the fact that the geomagnetic field is 3-5 billion years old. For context, the oldest known fossils of single-celled life on Earth date to roughly the same period. Life on this planet evolved, from the very beginning of its history, inside a magnetic field. The organisms that developed early photosynthesis that eventually oxygenated the atmosphere that gave rise through billions of years of evolution to every living thing on the surface today, did all of that under the protection of a field generated by liquid iron, churning in a core that was still young. The G-dynamo and the biosphere share a timeline. Whether the existence of a stable magnetic field was a precondition for life's persistence on Earth is a question that planetary scientists and astrobiologists study carefully, precisely because the answer has implications for any other world where life might arise. The rotation has been slowing for billions of years, driven by the Moon's tidal friction. It will continue slowing for billions of years more. In the very distant future, if the Moon and Earth survive long enough, the two bodies will become mutually tidally locked, each keeping the same face toward the other permanently, with a day on Earth lasting roughly 47 of today's days. That future is billions of years away. The current short-term acceleration, measured in milliseconds per day over a period of years, is a small fluctuation against this enormous backdrop. The inner core has been rotating and, presumably, oscillating between faster and slower rotation relative to the mantle, long before any instrument existed to measure it. The cycle of superrotation followed by subrotation documented in the seismic data may be part of a longer oscillation pattern that is repeated many times over the core's history. The 70-year cycle proposed in earlier seismic studies, if real, would have completed dozens of repetitions since the inner core first formed. The 2024 reversal may be one of many such reversals across deep time, invisible in the geological record because the signal they produce at the surface is too subtle to be preserved in rock. What is also true is that Earth's interior has been gradually cooling since the planet formed, and that cooling is changing the interior in ways that play out over timescales of billions of years. The inner core is growing, slowly, as the outer core cools below the solidification point at the boundary. The outer core is itself slowly losing heat to the mantle above it. Eventually, hundreds of millions or billions of years from now, if Earth follows a similar path to Mars, the outer core's heat flow may become insufficient to sustain vigorous convection, and the geodynamo may weaken significantly. Mars, smaller and with a higher surface-to-volume ratio, cooled faster. Earth's larger size has kept the dynamo running for billions of years longer. This long-term cooling is not detectable on any timescale relevant to human civilization. The inner core's growth rate, roughly a millimeter per year, accumulates significance only over geological time. The outer core's temperature change over a human lifetime registers in no instrument. These are changes happening in geological time, the time of mountains rising and oceans opening and species evolving. They are part of the same story as the changes happening now, but they are the deep background that makes the present moment intelligible. We are, right now, in the middle of a 4-5 billion year story of a cooling, changing planet. The instruments we have built are sensitive enough to see a few paragraphs of it in something like real time. What those paragraphs say is unusual by the short time scale of their measurement. Whether they are unusual against the full length of the story is a question the rocks are still answering. Tonight, the atomic clocks are still running, somewhere in the network of synchronized instruments that make up the International Earth Rotation and Reference System Service. The comparison between atomic time and Earth's actual rotation continues without interruption. The planet is completing each rotation either slightly ahead of or slightly behind the standard 86/400 second mark by amounts measured in fractions of a millisecond. And those fractions are being recorded and added to a dataset that now extends back to the 1970s. At some point, that dataset will be studied by researchers who will see in it the signature of whatever the inner core and outer core are currently doing, and they will understand it more clearly than we do now. The instruments will outlast the people who built them. The swarm satellites, if they remain operational through 2030 and beyond as planned, will eventually provide a dataset covering a generation of continuous magnetic field monitoring. The global seismic network, if maintained and expanded, will continue accumulating earthquake pairs that future researchers can use to track the inner core's behavior through the coming decades. The atomic clocks will keep counting, their cesium atoms oscillating at the same frequency they have oscillated since the clocks were first activated, indifferent to what the planet is doing on any given day. Somewhere in the outer core, 3,000 kilometers below the surface, liquid iron is flowing in convective columns organized by the planet's own rotation. The pattern of that flow has been shifting for decades. The flux lobe beneath Canada has been weakening, the lobe beneath Siberia has been strengthening, the magnetic North Pole, following the shift in that underlying pattern, has been crossing the Arctic at a speed that no navigator in the 19th century or the early 20th century would have considered possible. Compasses in the high Arctic are pointing somewhere different from where they pointed 20 years ago. The World Magnetic Model, updated in 2025, accounts for this. The next update, 5 years from now, will account for where the pole has moved since. Somewhere at the inner core boundary, 50,150 kilometers below the surface, the topography of the solid-liquid iron interface is, if the 2025 seismic analysis is correct, changing. Material is rising in some regions, sinking in others, altering the pressure distribution at the base of the geodynamo in ways that are beginning to be mapped from the surface through the echoes of distant earthquakes. A seismometer in Yellowknife, Canada, and a seismometer in Fairbanks, Alaska, are recording slightly different things when the same earthquake pulse passes through the planet. The difference tells a story about a place that no one will ever visit and no instrument will ever directly touch. And the inner core itself is rotating backward relative to the surface above it in a pattern confirmed by seismic data spanning 60 years. The reversal from the super-rotation it maintained from 2003 to 2008 into the sub-rotation it has sustained since approximately 2010 reflects a change in the forces acting on it, a change that connects through the outer core's fluid dynamics and electromagnetic coupling to the same system that moves the magnetic pole and maintains the field that deflects the solar wind. All of this is happening right now, as it has been for billions of years. The unusual thing is not any single measurement in isolation. It is the accumulation, 4 severally measured observations, each confirmed by independent instruments and peer-reviewed data published in some of the world's most rigorous scientific journals, all pointing to an interior in a state of change that is unusual by the baseline of recorded human measurement, possibly connected through a single system whose dynamics our models are still in the process of characterizing, happening at the precise moment in history when the instruments to observe it at this level of detail exist and are running. This planet is 4.5 billion years old. It has been doing everything described in this script for most of that time, in one form or another, without any instrument to notice and without any living thing to wonder about it. The field has reversed before. The pole has wandered before. The inner core has oscillated before. The rotation has accelerated and decelerated before. None of these phenomena are new to the planet. They are new only to us, newly visible in the light of instruments that are, by geological standards, almost impossibly young. On July 5, 2024, the most precise clocks ever built registered a day that was 1/66 milliseconds shorter than it should have been. No one felt it. No one's plans changed. The world continued exactly as it always does, but somewhere underneath it, in a sphere of solid iron, the size of the moon, surrounded by 260 kilometers of flowing liquid metal, generating a field that has protected this planet's atmosphere for 3.5 billion years. Something was different. The clocks measured it. The satellites confirmed it. The seismometers recorded it. Something really unusual is happening to Earth right now, and for the first time in the history of this planet, we have instruments precise enough to know, not to fully explain it yet, not to predict where it leads, but to see it clearly, in real time, as it happens. That clarity is new. The phenomena are as old as the planet itself. That knowledge is new. The phenomena are not. The planet has been doing this for billions of years, in the dark, without observation, without anyone watching. What is unusual is not the Earth, What is unusual is the moment the first generation of humans with the tools to watch the interior of their own planet in something approaching real time, watching it change, taking careful notes, and only beginning to understand what the notes mean. The notes are still being written, the clocks are still counting, the satellites are still watching, and the planet, indifferent and ancient and still turning through the dark, does not notice that we are finally paying close attention. Good night.